Okay, so we were started off looking at systems of equations, and we saw that there's a connection between solving a system and physical objects in space. And then we looked at solving a linear system with a constant matrix B, and we saw that that's sort of like finding the pre-image of a linear transformation. And then we said, oh, okay, what if that B happened to be equal to 0? And then we saw that the pre-image of 0 is something that we called the kernel. We switched to talking about vector spaces, and we started to talk a little bit about coordinates. And we saw that the great thing about having a basis is that we can write every vector in a vector space uniquely. Okay? So, let's continue from this point. So let's say that you have some vector space V. If you want to, you can think of this as Rn. And you have a basis. Let's call our basis capital B, and that consists of B1 through Bn, like this, right? Now, let's say you have any vector V in your big abstract vector space. So we know V is equal to A1, B1 plus blah, blah, blah plus AN, BN. And that we know that this is unique, right? And we know this works for every V. Okay, great. So what we want to do is we want to tie this idea. So let me copy this guy right here. Copy this down here. And now I want to say, okay, what happens if we have a linear transformation? Now that goes from V to W. So T is now going like this. Okay. But remember, T is a linear transformation. That means T respects addition, right? T of V1 plus V2 is equal to T V1 plus T V2. And it respects scalar multiplication. So that means you can factor K out of the linear transformation, right? So what this means is that if I took my any vector V, remember we said was some A1, B1 plus blah, blah, blah plus AN, BN like this. Then what we see is that when I apply T to it, I can use the linearity properties to break it up into pieces. And then that's going to give me A1T B1 plus blah, blah, blah plus ANT BN like this. So what's the meaning? What's the takeaway? The takeaway. T is completely understood. By simply looking at the image of the basis vectors. B1 through Bn. This is kind of amazing, right? Like imagine if you know what sine of 1 is, then this means that you know sine of x. I mean, that doesn't happen in the real numbers. Just because you know the image of a single number doesn't mean you understand the entire function, right? You know, so just because we know the image of 1 doesn't mean we understand sine of x for all x, right? So, but you know, sine of x is not linear. So of course that's not going to work. Okay? So this is just like a comment right here. So this is a comment. And that's just trying to capture this idea that, you know what, this is something that's amazing. It's not something that you should expect to happen sort of every day of the week. Okay. So, now we know that if I have a linear transformation, I could simply look at its image and look at the image of those basis vectors, and it's really completely understood. So then the next question is, what if I change the basis? How would T be affected? Can I write T in terms of a different basis? Right? So, that's a very natural question to ask, I think. In other words, when you have the standard matrix representation, okay, what do we exactly mean by that? Well, if you have your Rn over here, so it's Euclidean space, and then you have Rm over here, and you have the standard basis inside, that means that sometimes they call it S. S is equal to E1 blah 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 En, where E1 is like 1 0 0 0 0 0 blah blah blah. EI is like a 0 everywhere. And then for the ith guy is 1 ith term or ith coordinate. Okay, that's what I mean by the EI. And then over here you have the standard basis. And that's S is equal to, in this case, it's just E1 through EM, like that. Then when we take a look at this transformation, the standard matrix representation, A, this A is just, if you think of T of A, and we call A the standard matrix representation, A is nothing more than the images of TE1 through TEN. Okay. And that's going from the standard basis to the standard basis. That's what we mean by the standard matrix representation. So what we would like to do is we would like to look at a transformation that does not go from the standard basis to the standard basis, right? In other words, let's say that we had still a Rn down here. We still have a Rm over here. But I want to have a different basis here. I want to have a basis B1. And what does B1 look like? It's got basis vectors B1 through blah, 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 through Bn like this, right? And this has a basis B2. And B2 goes from, this is going to be a different basis. So I should call it maybe B1 prime, blah, 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 through Bm prime. Okay, so it's a completely different basis, potentially. And I want to really understand what is this matrix. So T is going here, and I want to know what's the matrix And we have an answer to that. So the answer to that is going to be something that we call M. We write it as B2, B1, because you got to do, the inputs are in terms of B1 and the outputs are in terms of B2. So what is this? What is M B2 comma B1? What it does is it takes as its input, the input is going to be coordinates with respect to B1. And the output is going to be coordinates with respect to B2. Okay, so how do I sort of get a hold of these coordinates? Well, we're going to go back up to this page, go back up to this diagram. I'm going to actually insert the earlier picture we had up here. So we're going to just put a circle here like this. This is still Rn. This is now standard basis, right? And this is the same T, it's the same action. It's still Rm up here, so this is still the standard basis. I'm not going to rewrite it. But you saw that the input needs to be coordinates. So what we got to do is we got to take our vector v up here, and we got to basically change it, find the coordinates with respect to b. So this is the coordinate function. And it basically is going to take v as its input, and the output will be coordinates with respect to the first basis, b1, like this. So books have also called this a transition matrix, because you're transitioning from the standard basis to b1. Okay. Same thing, we can also have another coordinate matrix, so we can make the coordinate matrix go this way. This is the coordinate function. And what it does is it takes any vector over here, we can call it W, I guess, and then it's going to take W and it's going to write the coordinate vector of W in terms of B2. Now, so this picture, you know, it's a pathway, so we can sort of have our path, you know, we could say, oh, this pathway is the same as this pathway, right? Or I could say, oh, if you first go down here and then you execute the transformation and then you change the coordinates back, then you'd have to find the inverse of that coordinate function. That would be the same as doing t, right? So if we were to try to take this version of the picture and I try to write down what it's trying to say here, okay, let me reintroduce this matrix A. This is the standard matrix representation. Then what are we trying to say here? We're basically saying that doing A is the same thing as, you know, first you do the coordinate function c b1 with respect to v, then you execute your m b2 b1. Remember, the reason why it's in this order is you're going from right to left, so you multiply by a coordinate vector in terms of b1. The matrix will output the answer in terms of b2, and then we have to go the reverse direction, so it should be c b2 of v. Really, it's the image. I don't have enough room here. Let me move this over. So we're taking the output there, and then we're going to change the coordinate back. So we're going to take, really, the input is going to be this whole thing here. And then it's going to be C B2 of that. But we have inverse, because we're reversing the direction of that orange arrow. So, so if you just thought of these guys in terms of matrices, then this is basically, you could call this transition matrix P. So let's call this guy P. Call this transition matrix P. Then what do we get? We get A is equal to P inverse MB2 B1 P. I meant to do that in blue. Okay. So, right, this looks a lot like, say, this is basically saying that the standard matrix A is similar to M B2 B1. Remember, we talked about similarity. Similarity was an equivalence relation. So this is a convenient place for me to stop.